everybody hear me well? Too loud? All good? Brilliant. Well, welcome everyone. How is jDays going? Good? Who is first time in jDays? Good. Wow, got a lot of people. First time in Gothenburg? Okay, so most of you have been here before, or maybe are from Gothenburg. That's pretty cool. It's my first time in Gothenburg. I'm fighting in Sweden. So I came with my girlfriend. We took this opportunity to explore a bit the city. We arrived on Saturday. It's quite funny because everything was, it was cold, but everything was sort of plain okay. And then on Sunday it started snowing, which for me was quite exciting because I am from the Mediterranean side of Spain, which means I don't see snow very often. I've seen snow in maybe 6-7 times in my life. And it was snowing all Sunday and Monday. So we went out and around, were really excited, decided to build a snowman. I didn't have experience building snowmen, so that was the first prototype. That's my girlfriend. You can see that really small thing. After that, then we decided to try another one, and then we got a little bigger one. As you can see, I'm very proud of my achievement, our achievement. Even though it's not quite what I was trying to do, I was aiming for something like this, but that's much harder than it seems. Anyway, so as you can see, my name is Abraham. I'm a Java developer and agile enthusiast. I don't like the word consultant, so I just say enthusiast. I've been working for the development industry in several different ways for about 10 years now. Currently, I am working at Mendeley, which is a company that does software for researchers, PhD students or postdocs, etc. If you're doing a PhD, you may want to check it out. I'm also a Java editor at InfoQ, where we write news about technology in general. I write about Java. And I also help run the London Java community, which is one of the biggest and most influential Java user groups. As an example, they are part of the JCP executive committee, which JCP is standing for the Java community process, which is the body that tries to set up the standards by which the community can help and contribute changing the way Java is done and defining the new versions of Java. In the past, I've also worked for JP Morgan and OpenBet. You've probably heard of JP Morgan, quite a big bank. OpenBet, maybe not that well known. It's a company that does software for online betting and gaming, and now also non-online and retail places. I wanted to mention them because a lot of the stuff, a lot of the ideas that I'm going to be talking about were actually developed or started to be developed while working at these places. So, the talk says continuous integration / continuous deployment. Now, many people understand different things when we talk about them, so I'd like to kind of establish what I refer to when I say this. So, continuous integration, I'm going to be talking about the idea of you check that everything's still working after you do a commit. So typically you would have a build system, you make a commit, and then it's going to build and run all the tests. And when I talk about continuous deployment, what I mean is that you do continuous integration, and after that you make a release out of it, or at the very least you make a releasable package. It's something that you can actually put into production or into a test environment, etc., at the push of a button. Some people say continuous delivery as opposed to continuous deployment. I myself sometimes exchange them. For some people, there are two different concepts. For me, they are the same. For the purpose of this presentation, it doesn't really matter because what I'm going to be talking is about the system itself and the pipeline and all the interdependencies, not about what happens with it at the very end of it. So, the talk is going to be divided on 3 parts. The first one is why you need to worry about having a continuous integration or continuous deployment system that is fast. The second one will be how you're going to make it fast. The basic idea, as you can see here, is by breaking down things, but we'll get into detail there. A bit of detail, not too much, unfortunately. And then finally, it's going to be about the what. The what being, once you have this system, and you need to tackle something, it's going to help you decide what you need to tackle in your continuous integration or continuous deployment pipeline. So, why? Let's think of a system, a build, right? So for instance, let's imagine I work for a company that is doing a web app. In my build, that web app is going to be deployed into Tomcat or something like that, which means my build produces an artifact that is a WAR file. Now, we just started, so this is relatively small. It has about 70 files, 800 tests. It builds in 4 minutes. I completely made up these numbers, but you get the idea. So then we progress. This grows. The application is bigger. The build time is larger. And it continues growing. And if we don't stop it, then our application is going to have more and more features, more and more checks, and therefore the build is going to take more and more and more, longer and longer. And then eventually this is going to become a problem. Let's do a quick survey. Who has automated builds, continuous integration or continuous deployment? Pretty much everybody, good. We don't have builds that take 10 minutes or less. A few, that's pretty good, pretty efficient. Between 10 and 30 minutes. Good, more than 30 minutes? More than 1 hour? Yeah, there is always somebody, don't worry about it. Which is good, this is why we need to think about this kind of thing. Now, the problems of size. The problem of size is, imagine we have a build that takes an hour. Let's go to the worst case. If I make a change, and my change breaks the build, I commit, the build is going to trigger. On average, it's going to take about 30 minutes, because on average, it's going to fail in the middle point. It's going to take about 30 minutes for me to realize that I broke it. Once I realize that I've broken it, then I'm going to take a look at the code. I'm going to see what the problem is. I'm going to identify the problem and push it again. And then it's going to start another build, which is going to take an hour to fully run, assuming it doesn't fail again. And after that full hour, then we're going to have a green build again. So that means that we have a span of an hour and a half where the build was red. Now, I'm assuming that my fix is actually going to turn the build back to green. But what if it doesn't? Now, if it continues to break, if it's red, now I have a problem, which is, I don't know if it is because my fix didn't actually fix the build. I don't know if it is because my fix fixed the problem, but actually caused another problem in another place. Or maybe my fix is perfectly fine, and it has nothing to do with me. It's just that in the time that the build was red, somebody else checked in something that broke the build, and because it was already red, we didn't notice. And now I don't even trust my own builds anymore. In very bad situations, what this tends to is somebody in the end stands up and say, okay, nobody makes any more changes until I fix the build. Once the build is green, then you can make your changes. Has anybody been in a situation like this before? Yeah, pretty common actually, right? So that's what I was mentioning. A red build means slow feedback. With slow feedback, that means that things can go unnoticed, and eventually you get to paralysis. And it's like, everybody stop, we need to fix this, and then you can continue working. So how do you manage size? I talked to a lot of people about this, because it's a problem that worried me, but I didn't know how to fix initially. And I found different ways that people tend to approach it. The first one is they just don't do anything. They just suck it up. They assume that builds are slow, and that's what you have to do. Now, as you can imagine, I don't like that option very much. The second thing that people try to do is they try to apply continuous deployment or continuous integrations kind of in a split way. So what they do is they separate the quick tests and the slow tests, and they say, okay, we're going to run the quick tests after every commit, but then the slow tests we're going to do on a schedule, for instance, every night. Now, that sort of gives you a faster build, but it also means that there are some problems that instead of knowing right after the commit, you're going to notice tomorrow when you come back to the office and you see the nightly run and you realize that it was broken. And then the problem that we talked about, that you broke something and maybe that hit something else, that's going to be exacerbated by this. A different approach is you get your application or your component and you divide it, you assign it to different teams, and then each of those teams is going to be doing continuous integration on the individual bits, but then we never put things together until we have to do like the big release, right? So once a month maybe, we actually check everything together, and then we realize that it doesn't work. So then again, this feels like a solution, but it actually makes the problem, in my opinion, even worse, because that means that before, it took me an hour to realize that I broke it. With the second option, it takes me a day. With the third option, it might take me weeks, depending on how long it takes to integrate all the pieces together. And then the fourth way that I found was by creating a test deprecation policy, which basically says, well, let's analyze the tests that we have. Let's find the ones that fail relatively often, the ones that fail sometimes, and the ones that never fail. When we locate the ones that never fail, if they don't fail, that means there's a part of the code that is quite stable, which means probably we're not going to break it, so we can just delete those tests. I didn't like that option either, because it feels like a nice argumentation, but again, I think it's very unsafe. It's a bit like saying, well, hang on, we have all these roads. It seems people don't have accidents in this road here, so that means we don't need safety belts there, because it feels like a safe road anyway. So I didn't like any of those options. What do I like? Here's where we come to the how. The idea that I wanted to have is to split the build into smaller bits and then only run the bits that I need. So for instance, if this is my initial build, the one that creates one artifact that is a WAR file that I'm going to deploy to Tomcat or whatever your web application is, then I'm going to split it in two, which means both are going to have reduced times. I know these numbers don't match up because in theory, when you split things, maybe you need to add additional tests for the integration part, etc. Again, I made that the numbers, it's just an example, so don't hang up too much on them. Anyway, the idea is I'm going to have now two different artifacts. Here is going to be some application backend.jar, and then here is going to be the original artifact, the WAR file. And the idea is that I have a system that whenever I make a change to the backend, then I'm going to run this build, I'm going to produce a new version of the artifact, I'm going to put it available somewhere, and then immediately after that, this next build is going to trigger, consuming the artifact that I just produced, running the build, and then producing the final artifact. Now that is if I change the backend. If I change this module here, the idea is I don't rerun the backend, I just pick up the latest available artifact, which is already built and already saved somewhere. And using that, then I run only this part of the build and produce a new version of the final artifact. That means that if I make a commit here, then according to these numbers, the whole build is going to take 10 minutes, which is actually even worse than before. But if I make a change here, then the build is going to take only 6 minutes, because it's going to be reusing a lot of stuff that we already built. Now, the actual mechanics of how you achieve this system, unfortunately, I don't have enough time in this talk to indicate it. The good news is I made a talk before about this, which you can check. It's there. There's a short URL. If you have smartphones, then you can just test that. Otherwise, there are all the talks out there that can show you how to do this as well. The whole point for now is that the basic idea of how you make your build faster is by picking the big builds and break them down into smaller ones, and then make sure that the build knows about the dependencies. So whenever you make a change, it knows what it needs to build and in what order to get to your final artifact. Okay? I'm gonna wait a second in case anybody wants to take pictures, and I'll carry on. Okay, good. Now that's gonna bring us to the what, which is kind of the point of this presentation is. At the beginning, things are going to be very easy. You have one big build, you break it down, that's it. When you have two of them, okay, that's still fairly easy. You get the biggest one of them, and then you break it down. But then eventually, you're going to get to something like this, or even harder, even more complex. This is a real case that I worked with. In this system, so at the very end, we produced 3 different WAR files that made up 3 different web applications. Every other bubble is a different build that produces a jar file. And then these 2 here, this is a login framework that also produces a jar file. And this one here is just a parent POM for the Maven builds of all the other ones, right? I wrote this way just because pretty much everything depends on this. So to avoid writing arrows all over the place, I simplify it like that. Now, by the way, one thing to mention, I'm talking about WAR files and jar files and Mavens, but this is just because I developed this using a system like this. But the ideas are going to be useful also if you use Gradle or you use C# or any other systems. Anyway, what I was saying is, when you get to a system like this, it's not going to be so obvious to know what you need to change to make the build faster, because it depends a lot on how your system is behaving. Is the problem that that build is too big? Is the problem that that gets changed too often and creates a cascade of builds? What's the problem exactly? So then when you get to this, you need to realize that you're talking about a performance tuning problem. And like with any performance tuning problem, what you need to do is, first, you need to measure, you need to understand how your system behaves, what the bottlenecks are, etc. Second, you need to establish a threshold. You need to define what your level of service is, how good your system needs to be, how fast. And then third, you need to monitor constantly, keep recalculating your values, and then whenever you go beyond that threshold that you have to find, then you need to start making little changes and remeasure until you're down the level again. Okay. Let's see how we can analyze these things. First of all, we need to, sorry. I'll pick that up later, sorry. Okay. First, you need to understand your system. In this case, the first thing I did was analyze all the commits in all the different modules over a period of 2 months. It turned out 28% of all commits came to that particular bubble. You may think that that's just an outlier, a particular case of my system, but actually, when you think of the way our team works, we tend to work in related features over time, right? We don't work on payments today and then something completely unrelated to payments tomorrow, because usually our new features are clustered around themes. And if your architecture is somehow sane, then changes to related features will go around the same pieces of code. So it makes sense that your changes tend to concentrate on particular bubbles. Now, the other thing to note is if 28% of all changes go to that particular bubble here, that means that those two WAR files are going to be rebuilt 28% of the time, because whenever we have a successful build here, then we're going to rebuild the two dependents. Of course, it will be slightly lower because sometimes that build will fail, and if it fails, then we don't trigger the other ones. But for the sake of argument, we can say that it just propagates like that. Now, then I analyzed what's the next most modified component. It turned out to be that one up there with 20% of time, which of course means that then that one is going to be rebuilt 48% of times, nearly half of them. You can start to see patterns. You can start to see that things concentrate. If you repeat this analysis for all the different components, and you check all the different frequencies, you can see how often you rebuild each particular module. And then you can try to graph it. The way I like to graph it is like a temperature map. So basically, you have colder colors for things that don't run often, and hotter colors for things that do run often, right? Things that we can see firsthand. The WAR files are the ones that seem to be hottest. They are the ones that are recompiled the most often. It makes sense because whenever we change something, eventually we're going to rebuild a WAR file. The parent POM on the login, very basic things. Therefore, we don't change them very often, which again, it makes sense. If your basic structures are changing very often, they're probably not that basic, actually. And then we see interesting things. Like, for instance, if you check here, it only has one dependency, but it's significantly warmer than its dependency. That means that, well, obviously, if we change this, we'll rebuild that. But we are rebuilding this one more often than that one. That means that the reason we're rebuilding it it's not because of its dependencies, it's because we are changing it. We're making code changes to this component. So that's telling us something. That's telling that maybe these ones, if receiving too many changes, take a look at the other ones. These all directly or indirectly depend on this one. And they have roughly the same color. That means that they're being rebuilt roughly the same number of times. If they're being rebuilt with the same frequency, that means that these here, they are not being rebuilt because we're changing them. They are just being rebuilt because its dependency was modified. So probably that means that this one is containing too much logic. That's why we're changing it a bit too often, and that's why there are so many things that depend on it and need to be rebuilt even though they're not being changed. Okay, so we begin to get some information with this kind of thing. Now, let's try to add some more information. So we've talked about frequency. Let's talk about duration. How long do builds take? We can shape the different components in our graph depending on the build duration. Again, some very obvious things. The WAR files, those builds are the ones that take the longest because it needs to build a WAR file, and at least the way we implemented it, we had to deploy that WAR file into Tomcat and then run a number of integration tests against Tomcat, which takes much longer than unit tests. The POM file, really tiny, makes sense. There's not even code there. It's just an XML file that needs to be parsed, and then we can put it up. Oops, sorry. And then look at this one here. It seems bigger than the ones around, which is adding weight to the fact that, or to the idea that maybe that bubble is doing too much, and maybe that's a good candidate to tackle in the next iteration. Now, there's a problem with this, which is this is all relative to each other. So yes, it is true that if I had a problem with speed and I had to break things down, maybe that's a good candidate to start looking. But the question is, do I have a problem? Then this is when we need to start looking at the things overall. I'm going to present a number of metrics that I find useful. The first one is what I call the build time. Now, the build time is pretty obvious. It's the time it takes for one build to execute. And then the change rate, which is how often we modify a particular build. Now, this is not how often I rebuild a particular component. That's what we represent by the colors here. This is how often we change. We make code changes to that component, which is kind of that 28% that I talked about at the beginning, right? Okay. With that, we can build on and we can construct other things. Let's say we have a system like this. So we have build A, and B and C depend on A. That's why these arrows in the pane triggers. Now, there could be other builds hanging off here as well. We can define the impact time as the time it takes for a build and all its subsequent builds that get triggered to execute. In other words, impact time of a build is the time it will take to clear up or rebuild everything that needs to be rebuilt if I make a change to that particular build, right? The way you calculate this depends a bit on how you have set up your system, or more specifically on whether you can run builds in parallel or not. If you cannot run builds in parallel, that means that the build time of A is going to be, sorry, the impact time of A is going to be the build time of A, how long it takes to build, plus the impact time of its direct dependencies. Right, so how long it takes to clear that up and how long it takes to clear that up. If you can run things in parallel, then it's actually going to be the maximum of the impact time of those two. Again, this is a bit of an approximation because it could be that then these two builds end up triggering the same one, which means those impact time have some overlap. But just to know, just to assess how the system works, is a good approximation. Now with the impact time, okay, now let's see how the impact time evolves in the graph. So the impact time will grow as we go left, because the impact time of each bubble will include the build time of its dependence. So then there's a curious thing, which is the POM file that everything depends on. That means that's going to have the smallest build time, but it's going to have the highest impact time, because whenever you change the POM file, you're going to have to rebuild absolutely everything. You could maybe do another graph in which you show the impact time as opposed to the build time, but that depends on what your needs are. Okay, we go to the next one, which is the weighted impact time, which is the impact time times the change rate. What this is telling you is, you know, the typical discussion, we should change this module because it takes very long. Oh yeah, it takes very long, but we don't change it very often, so maybe that's not a problem. Or the other way around. We should change this problem because it runs a lot. Well, yeah, but it's very fast, so maybe that's not a problem. So this is going to give you a way to compare the different builds, taking into account how long it takes and how often you change them. And then when you put them all together, then you come with the average impact time, which is going to be a measure of, on average, how long it takes for your system to clear up whenever you do a change anywhere. Right, so these metrics can give you the big picture of how your system is behaving. With that, we can start creating some thresholds. For instance, your average impact time could be a threshold. Maybe you say, on average, I want my builds to take less than 10 minutes. If every now and then it takes an hour, because we're doing something very extreme, that's fine, as long as it doesn't happen often. But on average, I want my impact times to be 10 minutes. You keep measuring this. If at any point it goes over 10 minutes, then you can start checking the temperature graph, etc., to see where you need to tackle the problem. Another example could be the maximum impact time of all your builds. Does anybody have particular SLAs of time, service level agreement? Something like, if there is a problem, you need to fix it within, I don't know, 10 hours or something like that? Good. Now, the problem with that kind of SLAs is, imagine you need to fix something like a priority 1 bug within 10 hours. If your build takes 1 hour, that means you only have 9 hours to find the problem and apply the solution, because the last hour is going to be rebuilding. So maybe what you want to make sure is to be able to have as much time as possible to find the problem and create a solution. You want to make sure that your maximum build time is bounded. So that will be your measure, your maximum impact time. So that's how long it's going to take in a worst case scenario. With that, with your thresholds and your maps, you can start analyzing things, and you can keep your continuous integration or continuous deployment on track, and you can make sure that it's going to be the bottleneck of your team. This has one problem, which is all these calculations that I made, I had to make manually. Right? I've been looking for different tools around to see. Okay, sorry. I've been looking for several tools around to see if I could create these graphs or if it could give me the different numbers. The problem is there is nothing that, or at least I haven't found anything that gives you quite these things. There are different tools or different APIs that will give you parts of this information. The good news is, it's not particularly complicated, so we can try to automate this. So whatever CI system that you use, Jenkins, TeamCity, etc., most of them have an API, so you can start consuming the data. The calculations that I'm making, they're not particularly complex, and there are several tools around that you can use to graph this. So in fact, I've started giving it a go with JavaFX. I've never done JavaFX before, so it might not be the best system ever, or I think it's a bit buggy. But well, if you'd like to give it a go, what I'm trying to do here is, at the moment, it connects to a Jenkins instance, and it can't get data from all the builds and create the graph. And it can't do the temperature mapping. It doesn't do the sizing yet, and it doesn't support the build systems either, but it's a start. If you'd like to contribute, well then welcome. Oh yeah, well actually I've had a color, I need to update that. These are the next things that I'd like to do. The reason I'm putting this out is because I really think that people are not paying enough attention to the continuous integration build. It feels like something that people put at some point and then think, yeah, that's fine, we have continuous integration now, we're good. But I've been talking to many people, and I like to continue talking to people, and I've been hearing a lot of experiences, and it's not a trivial problem. I don't think we can do one single application that will fix everything, and most importantly, I don't think anybody can tell you what exactly you need to change in your system to make it faster. The only thing that we can do is we can give you the tools so you can analyze your system and then decide what you need to change next. So that's pretty much it. I think it was a bit shorter than I expected. The main takeaways is, first of all, continuous integration, continuous deployment can be a big, big bottleneck. You know, these days it's all about agile and time to market and responding to things. And there's no point in trying to do iterations and short stories and everything if at the end what really slows you down is your continuous integration environment. And if what really slows you down is your continuous integration environment, then you need to put the time and the resources to invest on it and make it faster. Making it faster is difficult. It's like any performance tuning application, and you need to think about that. It's not just making guesses here and there. You need to systematically measure things and understand how your system works. There are not quite tools out there, but you can help me and build one. So I believe that's a bit shorter than I thought, but that means that we have some time for questions, maybe? Oh, yes.
I imagine that the system you're thinking
Oh, hang on, there's a microphone coming.
I imagine that the system you're thinking of is a monolith. It's a big wall of mud in terms of code, rather than a microservice environment where effectively you have everything's decomposed into small chunks of code, and each one is deployed individually. So is that am I thinking correctly to make that assumption?
Not necessarily.
No?
I'm going to try to go back to the system. Okay, so in this case, we had 3 services being produced. I don't know if I would call it microservices. They weren't that micro, to be honest. It is true that if you have one single big monolith, then in the end, instead of 3 different bubbles, you're going to have one bubble. Yeah. That is true. However, it doesn't mean that the different components that make up your big bubble at the end, they cannot be broken down. So you may have some difficulties breaking down the last bit, but what you can try to do is make the last bit just an aggregation of individual components, and then just some basic smoke tests to make sure that the different components are happy with each other. But then all the other logic can be put back in other components. And then it's just a matter of making sure that the different components are small enough, or the dependencies between the different components are same enough, so your average time is better. Again, in the end, it's all about measuring and establishing the threshold. So if you get to a point where you reach your threshold, then that's fine, and it doesn't really matter if in the end you have one monolith or many microservices.
Okay, thank you.
No problem. Then there was, yep.
Actually, I'll go back to the monolith system, where assume that it's a big monolith system, and the thing that you use to build is Ant, not even Maven, so you don't have the Maven repositories. And then can you actually explain how I should break the big monolith build into these bubbles? Because I mean, you have Ant as your build tool, and you have you're downloading all the dependencies at one place, more or less. It's not even segregated in different modules.
Right. So you have Ant. Do you also have Ivy?
Oh, sorry?
Do you use Ivy with Ant? Ivy is, I think, is a dependency management for Ant.
Yeah, maybe. I think it's that.
Okay.
Because most of our dependencies are being downloaded using Ant, or we have the script for that.
Okay. So with Ant, it might be a little bit more difficult because it's just more like an automation task tool rather than a dependency management. However, the key thing is that you can reuse things that you have already built. So I would say that the first step is either create your own tasks in Ant, so you can, at the end of a build, get the binary and deploy it somewhere where you can reuse it later. Because the key thing of saving is reusing things that you have already built, so you don't have to build them again. If you keep on rebuilding things, then it's very difficult to have saving. It's the way I like to express it is that the most efficient build is the one you don't need to run. So then the key thing is trying to have things that you don't need to run. I think there was another question around there. Yes.
I really like the visualization you got in back of you right now. But could you once again explain the difference on what you represented by size and the connection to not rebuild rate but change rate?
Right. So hang on, can you repeat the question again?
So you got the color is the rebuild rate.
Right, yes.
And you also had the change rate, and you have the size of the bubbles. Could you just reiterate on those things?
Yes.
Because I think you captured a lot of interesting stuff in one graphics here.
Yeah.
You just could elaborate.
So in this graph, there are mainly two dimensions being graphed. Or you could say 3, even 4 dimensions, depending on how you call it. The first dimension would be the builds themselves. The second dimension would be the dependencies. Now, the dependencies go in the opposite way to the arrows. So what the arrows are actually representing are the triggers. Whenever I change this, if it gets modified, then all the builds will get triggered. And then this will get triggered, and then in the end, we'll rebuild the WAR file. The third dimension is the color. The color is, in this case, representing the frequency of rebuild, which is not necessarily the frequency of change, because you could rebuild it either because you're changing it or because a dependency has been changed. You could change this to a temperature map that shows change rate if so you want it. Sorry. And then finally, the size represents the build duration, how long it takes to rebuild. Again, you could change that if you needed to, for instance, the impact time, which is how long until everything has been cleared out whenever you make a change to that one. So it depends a bit on what you're trying to figure out, and maybe the best thing would be to have all of them. And then you take a look at all of them, and that's going to give you the picture of how your system behaves. It's a bit like, does anybody do garbage collection tuning? Good. So as you probably know, it's a very hard, dark art. And one of the most difficult things is actually understanding what's going on in your memory, how the objects are being promoted between the different regions, etc. And one of the things that you need is to see things, to visualize them. This is what the graphs are trying to do. Does that answer your question?
Yeah, I have a quick follow-up question. Have you used any specific tool for this, or have you just generated graphs and plotted them out? What you've got in back of it.
Oh, what this? Yes, a very specific tool is PowerPoint.
Okay.
So this is what I'm trying to create the other tool to automate it, because basically what I had to do is first get the logs from subversions, then split that, put that into a spreadsheet. In the spreadsheet, calculate how many times each thing is going to run the other one. I had to put the dependencies manually so as to calculate how many things each thing was being rebuilt. Then create the colors, apply the colors manually, also draw the dependencies manually, etc., etc., etc. The problem with that is that, okay, maybe you can spend one morning or one day to do it, but then that also means you're not going to do it very often because you need to do your normal work, which means maybe you're going to do it once a week or once a month. Depending on how fast things change in your team, that might be enough, actually. Maybe you just need to review things once a month, and then you make a call. If you need to do it more often, though, or looking into the future, if you want to make your build thresholds part of the criteria of a passing build, then you need to automate it. And for that, I haven't found the tools yet. Any other question? Great. Well then, in that case, thank you very much. I hope you enjoyed it. If you like.